Now, as promised, we're going to take a look at some visuals of these polar plots, and I think you're going to enjoy some of them. Now, to add a little bit more to what you're going to see, I'm going to kind of juxtapose the rectangular plot alongside the polar plot. Same equation, but just different coordinate systems, and you're going to see very different results, right? So obviously I'm using my trusted sidekick Maple here, much better at plotting than I can ever hope to plot. And then, so you can sort of ignore all the code. But what I will do for each of the plots that we're going to look at, I'm going to tell you what the equation is, right? So for the first plot that we have here, on the left-hand side, it's going to be y equals 2 sine of 3x. I'm just using y and x are standard variables. And then on this side, then, on the right hand side, it's going to be r equals 2 sine of 3 theta. So remember, in the rectangular coordinate system, our standard variables are x and y. In this polar coordinate system, the standard variables are r and theta. But it's the same exact equation, just plotted in a different coordinate system. And I'm just going to play the animation for each, and we're going to see the graphs as they're traced out. So I'm going to start by looking here on the left, and what I'm seeing is a standard sine curve. Yeah, there's the amplitude is a little bit different, the period is a little bit different, but yeah, here's a basic sine curve. And now what's going on over here is a polar curve being plotted, but this doesn't look anything like what's on the left, right? You can see as it was tracing out, as it was going from, in this case, it went from 0 to pi, we ended up getting these, and we call them petals. This is an example of a polar rose, right? The flower, a rose. And then we have the number of petals here. So when you look at these two plots, right, you would not, if I took everything away and just showed you these two pictures, you wouldn't guess that it's the same equation, right? But it's the same equation. What's different is the coordinate system. All right, so what's the next one? So the next one is another kind of trig function. This one has some like vertical shifting, and I think some vertical expansion or stretching going on as well. But on the left, you're going to see y equals 2 minus 2 sine of x. And then on the right, you're going to see r equals 2 minus 2 sine of theta. And let's go. Let's see what's going to happen. And so again, another kind of a typical sine curve on the left. But when we look at what's going on the right, that doesn't look typical at all. And now the reason why it is a little bit slower on the right is because it's using a few more frames just to make sure that everything is nice and smooth. But look at that resulting curve. It looks like a heart. In fact, that polar curve is referred to as a cardioid, you know, and there's the heart reference. But again, when you compare these two just side-by-side plots, they should, you get the sense that, yeah, they shouldn't be at all related, but they are very related. The only difference being one is rectangular and the other is polar. All right, so that's our second one. Now, I think the remaining ones, we don't have any more. Well, this one doesn't involve a trig function at all. It's pretty simple. On the left, you're going to see the plot of y equals 2x. Now, if you think about y equals 2x, that's a simple linear function. So we would expect to see a line on the left. And then on the right, we're going to see r equals 2 theta. And let's see what that polar curve results in. All right, so let's play. And there we go. We see the line on the left for sure, and I am definitely not seeing a line on the right. In fact, it looks like we're seeing a spiral. And notice it started at the pole, which is just another name for the origin, and then it's spiraling out. It's like the radius is getting bigger and bigger, and it is because the equation is r equals to theta. So whatever the angle is as you go around and round, and your theta goes from 0 to, let's say, pi over 2 and pi, you're doubling that theta. So you're making it twice as big and then using that number to represent the radius. So yeah, the radius is getting bigger, and that's why you start at the origin and then you just kind of spiral outwards, right? So, but look at the comparison, line versus spiral. I think the spiral is really cool. All right, this one, I think it's going to be another spiral, but this one is actually going to start at a positive radius and then spiral inwards, right? So the equation on the left is going to be y equals e to the negative x, right? And we know what that looks like. Roughly, we should know what y equals e to the negative x looks like. Well, what is r equals e to the negative theta going to look like in the polar coordinate system? One way to find out, let's have Maple do our plot. All right. So yeah, you can see on the left, pretty standard exponential curve. Now look at the polar plot. As I said, it started somewhere. It looks like at a radius of 1 actually, which would make sense, because when theta is equal to 0, e to the I theta will be equal to 1. So it starts out at 1, but then the radius gets smaller, so you're kind of spiraling inwards to the origin. Now again, it doesn't look quite as mystical as the previous ones where you saw lots of polar points being plotted. Well, the thing is, there are lots of points being plotted. The thing though is, notice how quickly the e to the negative x function on the left, how quickly that graph approaches 0. Same thing here. Then what that means is that your radius is going to approach 0 pretty quickly. So it's like all the points are very, very close to the origin or the pole, and then you don't really see it. It's not easy to visualize that, right? So maybe not as spectacular, but still very different when you're plotting your e to the negative x versus e to the negative theta. All right, so we got one last one, and I am pretty sure this one is going to be your favorite, right? Now the equation is a little bit more complicated. I've combined the exponential. I've combined, this one has the sine function. It has the cosine of 4 theta. So all of that, right? So it's a little bit more complicated. So let's just see what the two resulting graphs are going to be. So let's play. And so on the left, again, with the function including sine and cosine, it's somewhat expected to see the peaks and valleys like this. But look at what's going on the right. That what's taking shape there? Can you fathom a guess? That looks to me like a butterfly. And yes, in fact, you can define the graph of a butterfly in a polar coordinate system rather easily, right? So trying to get this sort of graph in the rectangular coordinate system, very, very complicated. But yeah, you can get it quite easily in the polar. Now, how did we figure this out? Well, it's just kind of trial and error. You kind of play around, you let the software do all the work, you change some parameters and see how that affects the graph. But yeah, pretty cool. So now that you at least can visualize some of these polar equations and then kind of compare them to the rectangular counterpart, when you think about what our main goal here is to do or to determine some of the calculus properties of these curves, so for instance, like our simple exponential spiral here. What if we just drew a tangent line and I wanted to know the slope of the tangent line, right? At a particular point, at any point here, right? Because it's nice and smooth, nice and differentiable. How would we do that? Same thing here. You know, you could pick a point on the spiral and construct the tangent line and see how what is its slope. Or another interesting question might be, how long is this spiral? Let's say you could magically pick up this spiral and just kind of straighten it out, and it's like this long piece of string. Like, what is its length going to be? So how long is, you know, one of these polar curves? Well, that sounds like a calculus problem. Now, if you had to find the length of this line segment over here, you wouldn't need calculus. You could just use the distance formula or Pythagoras to find the length of this linear graph. But you can't use geometry when your graph is nice and curved like this. And then another important question. So we have a heart here, right? We have this heart. Now, suppose we could say that whatever amount of area is enclosed in our heart is a measure of the magnitude of the love we have for something or for someone. So like, how much love do we have for that person or that thing? Maybe we want to find the area that's enclosed inside this polar curve. Well, that sounds like a calculus problem. We know what area is and kind of looks like in terms of the rectangular, right? It's the area that's between either the curve and the x-axis or the curve and the y-axis. Or it could be between multiple curves if you really want to get complicated. But yeah, if we just wanted to figure out the magnitude of our love, we might want to find the area that's inside this heart. And then you could also ask the area problem for our rose. Like, what is the area, maybe in just one petal, right? And if we could figure it out for one petal, by symmetry, we could say, okay, well, how much area could we enclose inside this entire rose, right? And again, the way you could say, well, what would the area represent? Well, if you were to paint the petals, how much paint would you need to paint the entire rose or some fraction of that rose, right? So hopefully, you know, with the help of Maple, you can now see just how different, even though we plotted this exact same equation in each of these examples, by plotting them in different coordinate systems, we ended up with very different and in some cases very interesting curves. And in the subsequent videos, we're going to look at the calculus of these curves, because that's what we really want to get into. As cool as the pictures are, the calculus is even cooler. So I'll see you in the next video.